The following is a tutorial for how to calculate truss forces, and what I have here is a beautifully designed worksheet to help guide you through this process. So anytime you're sitting down to do a truss force calculation, you're figuring out your reaction forces and then all of your compression and tension forces in the truss, it's good to do this by hand because there's a lot of visualization as a part of this process. So get yourself one of these worksheets. We'll have printed copies available in the classroom. I also have it linked on the daily schedule. But to get started, let's go ahead and draw out a truss. So for this example, we're going to start very basic and we're going to do a three-sided truss. So I'm going to draw that in first. Just make a nice triangle here. And then we're going to label each one of those points A, B, and C. Those are going to be the member joints, and then we have the members themselves. And this is going to be member AB, so we can just go through and label all of that. Member BC and member AC across the bottom here. So that's the first piece of the puzzle. Now, what kind of supports do we have on this truss? More often than not, we're going to have a pin and a roller. And with the pin support, usually denoted with a triangle, you're going to have two reaction forces. So let's draw those reaction force arrows in and label them properly. Reaction force at the joint A in the Y direction, so RAY, and then reaction force at joint A in the X direction, RAX. Over here at the roller, we're going to have one vertical reaction, and that's going to be labeled reaction force at joint C in the Y direction. So we have that on there. We also need some applied forces. We're going to do two applied forces on this, which is kind of next level. So we have P1 on joint B coming straight down, and then at joint B as well, going off to the right, we're going to have P2. So we're just giving those the label P1 and P2, and then specifically P1 will be 650 pounds, and P2 will be 600 pounds. So that's most of the setup. We do need some dimensions on this truss. We need to know how large it is. So we're going to add that as well. I'll do that in a different color here. I'll make it in green. And for the dimensions, we're going to say that the height of the truss is 12 feet. And then across the bottom here, we're going to call this entire dimension 25. So from A all the way to C, 25. And then down the middle here, I'm just going to draw an imaginary hidden line, so a dashed line there. And then just to break this into two smaller segments, we'll call that 16 feet on the left and 9 feet here on the right. So we're getting closer. We have almost all of the information. What we will need as a part of this process is going to be our angles, our interior angles here. So we need to know this angle here on the left at joint A, and we need to know this angle here at joint C on the right. To figure that out, we can do inverse tan and use the dimensions here to figure out what those numbers should be. So for joint A, we're going to start off with A's angle is equal to, so A theta equal to inverse tan, and then it should be opposite over adjacent. The opposite side of this angle is 12 and the adjacent side is 16. So we're going to put 12 over 16 here. Now that comes out to 36.87 degrees, and then we can go ahead and label that here as well. 36.87 degrees. Now for theta C, we'll list that over here, and again we'll do inverse tan. Its opposite side is also 12, but its adjacent side is 9. So this time we're going to do 12 divided by 9, and that angle is 53.13, so 53.13 degrees. And again, label that here on your drawing, 53.13 degrees. Okay. So now we have enough information to move forward, and the very first question that we want to answer is the static determinacy. The formula for this is 2J is equal to M plus R. J stands for joints. There are 3 of them in this. So we have 2 times 3 on one side. M stands for members. We also have 3 members, AB, BC, and AC, so 3 there. And then R stands for reactions, and we also have 3 of those, 1, 2, and 3. So static determinacy means that if we equal each other, which in this case we do, 6 does equal 6, we are good to go, then we have enough information about this truss to move forward through this entire process. If these numbers do not match up, it would be called statically indeterminate, and that means there are too many unknown variables. It's probably also a poor design, and we would not be able to complete the process. So you might be thrown trusses along the way, either by myself or on the end of this exam from Project Lead the Way, that are not determinate. Do not waste any more time going through the process. You won't find the answers to the variables. So from here, the next step is called sum of all moments. And what we want to do is take your thumb and put it on the joint that has the most unknown variables. Here is joint A. We have 2 reaction forces. That is the most unknown variables at any particular joint. So we're going to put our thumb over that and call that the pivot point. While that is covered, you want to examine the rest of our drawing and identify the remaining force vectors. Here we have RCY, P1, and P2. So these 3 vectors are all going to be included in this calculating moments formula here, sum of all moments. So all 3 of these, P1, P2, and RCY. And then we have some reminders here that clockwise is going to be negative and counterclockwise is going to be positive. So as we draw this out, let me grab a red pen here. If we think that A is the pivot and RCY was going to rotate around the pivot point, we could expect its rotation to go that direction, and that is counterclockwise, CCW. So I'll put a little label on there to remind me that it's positive. Now P2, if left unopposed, is going to eventually rotate around this way, around A. That is clockwise, CW, and should be considered as a negative value. P1 is also going to do the same thing. A little bit easier to visualize. It's going to come straight down around A and rotate this way. That would be also clockwise and negative. So we have that labeled. Let's fill in the formula. Sum of all moments equals 0. Sum of all moments equals 0. List out the moments, P1 and P2, and they're both negative. So minus P1 minus P2, and then RCY is a positive, so plus RCY. Set that equal to 0. Every moment has 2 things, a distance and a force. So what is P1's distance? Looking at our drawing here, P1's distance to joint A, perpendicular to the direction the arrow is facing, is 16. So let's add that. P1, I'm going to say negative 16 times by its force value of 650. That's the first half. Next, P2 minus P2. Its perpendicular distance to the plane of rotation on A is 12 right here. So I'm going to do negative 12 times by its force value of 600. And then RCY, so plus RCY. I know the distance from RCY to A is 25 feet overall, so that's the distance I want to put in here. But then I don't know what RCY is, so I'll say multiply by RCY, set that equal to 0, and then we want to solve for this variable, RCY. It turns out RCY will be equal to 704 foot-pounds. So that's our reaction there at RCY. Now, the next step is to remove your thumb from joint A and evaluate all vectors in the y direction. So sum of all forces in the y direction equals 0. That's our next formula. So that should just be written as sum of all forces in the y direction equals 0. All right. let's go ahead and identify those. We have RAY, we have RCY, and we have P1. And that should equal 0. Now another one of our guiding principles here is when we're looking at vectors, if they're up and to the right, they're considered positive. If they're down and to the left, they're considered negative. So RAY and RCY have both been drawn pointing up, so they're positive. I'm going to put a plus symbol between those two. But then P1 is in fact pointing down. So that's going to be denoted with a negative vector value there. So minus P1 equals 0. At this point, just plug in what we know about these values. We know RCY now is 704. And we know that P1 is minus 650, and that should equal 0. We're going to figure out what RAY should be. So simplify this and solve. RAY is equal to negative 54 lbs. Once we have that value, we can then look at the x. The x can be a lot simpler. If you don't have any applied forces in the x direction, if this P2 was not here, your answer is just 0 because there's no reaction for it to have. In this case, we do have a vector going in the x direction, so we're going to do some simple math for this real quick. List all of those things out. The formula looks like this. Sum of all forces in the x equals 0. What are those forces? We have RAX and we have P2. Both of those vectors are pointing to the right, so that's going to be positive, so I'll just put a plus symbol between them. I know that P2 is 600, so I can substitute that. RAX plus 600 equals 0, and then simply move the 600 over. So RAX is equal to negative 600 pounds. Okay, so this in red was what we just did in the previous lesson for calculating moments. Blue was new for this lesson, static determinacy, because it relates to the whole truss. Now we have to go to each joint and calculate out our member forces. So this is where force vectors from the previous lesson will come into play. So here we have a spot for you to draw this out. I'm just going to label this cell as A. I think I'm going to switch back to black for the drawing. So at joint A, you want to redraw the truss down here because we're going to add a few more labels, a few more numbers. So I'm going to just draw out that side of the truss, label it all A, B, and C accordingly. I'm going to label the members as well, A, B, and AC. I'm going to add in those reaction force values because we're going to need to reference those. So RAY was equal to negative 54. And RAX was equal to negative 600. We got those in there. And then have our angle that we know as well. So I'm going to put this down below, 36.87 degrees. And if you remember back to force vectors, if you have a vector that's on an angle like AB is, it has two component forces that got it there, a vertical and a lateral movement. So when I'm doing trusses like this, I like to draw my component forces on the outside of the truss. So I'm drawing in these component forces, and I'm going to label them ABX and ABY. We need to use those. We're going to run through SOHCAHTOA, some sine and cosine with that, and figure out what those vectors are, and then eventually be able to identify what AB is as a part of this process. So additionally, because I decided to go outside of the truss, instead of using 3687, I have to use the reciprocal of that for the 90 degree that we have over here, which ends up being 5313. It's the other number that we calculated up here. So simple application 5313, and that's actually the number I will reference when I'm doing my work over here at joint A. So let's get into it. Sum of all forces in the y direction equals 0. List all of the force vectors that we have here in the y direction. You have RAY and you have ABY. Both vectors are being drawn up, so I'm just going to list out as positive, but as I substitute in what I know about RAY, it will carry that negative 54 with it. So I have negative 54 for RAY. And then ABY, Y is the adjacent side of my known angle. AB is the force that I need to solve for. So we're going to say plus AB, and then we're going to substitute Y for cosine. We're using cosine because in SOHCAHTOA, C-A-H, A stands for the adjacent side of the triangle. I'm also then going to attach the angle 53.13 and set that equal to 0. So we're going to do some moving around, some simplification with this. I'm going to just give you one step. We'll say AB is equal to 54 divided by cosine 53.13. And ultimately, AB is equal to 89.99. If your final answer for this is positive, that's considered a tension force. So please label that as well, tension. If our result comes out negative, it's considered a compression force. So I just want you to label that as well. Positive results are tension, negative results are compression. So moving on to the next cell here, sum of all forces in the x direction. I can do AC from this joint as well. I can get it from joint C, but I already did all my drawing here, so I'm going to solve for it here. Sum of all forces in the x direction. I have RAX, ABX, and then member AC itself, because it is moving along this vertical path. This lateral path here, I should say. Sorry, not vertical. So let's list those out. I have member AC itself, and that's what I'm going to eventually say is equal to from this setup, plus ABX plus RAX equals 0. Substitute what I know. AC I'm going to solve for, so I'm going to set that equal, or just add that in over here, and then say plus AB I can substitute for the value that I just calculated. So 89.99. With that, we're looking at the x side of this, so I'm going to use sine now. So sine of 53.13. And then just to really hit on that one again, I'm using sine because it is the opposite side of my known angle 53.13, and SOHCAHTOA, so S-O, O stands for opposite side. So I'm using sine here. And then I just want to add on that negative 600 from RAX and say equals 0. So I'll do some simplification here inside the parentheses. That comes out to 71.99, and then I'll just say minus 600 equals 0. AC, when it's all said and done, should equal positive 528. And that's, again, a positive result, so tension force. Okay. Now we have two of our member results. We know AB and AC. The one that we don't know yet is BC. So we're going to go find that. To do BC, we do need to redraw the truss from the C's perspective. So I'm just going to move my sheet up a little bit so you can see the bottom here. And let's redraw that very quickly. We're going to add our angle in here. I'm going to label B, C, or sorry, that's A. C's in the bottom right. And then remember, BC is the thing that I want to solve for. I'm not even going to bother doing AC down here because I already know it. So just BC. And then we can add the reaction force, RCY, and that it equals 704. So record that as well, RCY and 704. Give that a nudge. And then our component forces here for BC. So one going up and one going to the left. I have B, C, Y, and B, C, X. Those are the labels for the component vectors. Lastly, I will include the angle here. So that's 36.87. Again, we did calculate the interior at 53.13. The exterior complement is 36.87. So we have all the information we need now. And if we look at sum of all forces in the y direction, we can start to address this. So RCY and BCY, those are the only two things I have happening in this y direction right now. List those out. RCY plus BCY equals 0. RCY I know is 704 plus BC, that's the thing I want to solve for, and then we're going to do our cosine application here. So y, I'm going to replace y with cosine because it is adjacent to my angle that I'm using, and then the angle itself, 36.87 equals 0. When we run this through, BC equals negative 880. That is a negative response, so compression, and just label it comp. And now you have completed the truss. You've figured out its static determinacy. We did the sum of all moments to get the first reaction on the C joint. Then we did sum of all forces in the y direction to get the reaction at joint A in the y. Sum of all forces in the x over here to get RAX. And then we went into each joint. To review that process, it was isolate joint A, draw everything that is relating to joint A, include your component forces, run through sum of all forces in the y, list them out, find that magic number, sum of all forces in the x, list them out, find the number, and then you move on to the next one. Depending on the complexity of the truss, one thing I will end on the fact that you will probably get into the habit of doing y first and then x, but depending on the configuration, you might find that you're going to list a whole bunch of things here for y and actually end up needing a number, or two numbers I should say. And the solution to that is to actually do the x first. Do the x first, list all those out, and realize, oh, I only have one missing variable here. I take this value and then plug it into here to figure out that value. So it doesn't always go y and then x. Sometimes x comes before y. It just depends on the configuration of the truss. So hopefully this would be a nice guiding video for you on how to do this entire process. And I wish you all luck. Of course, the trusses that you will be working on will grow in complexity from here, but this is the basis of it and the starting of it. So hopefully this was helpful to you all. I will see you next time. Thanks for watching.